why is this, by the way, why is this so important? Again, it's because we measure distance in 2 dimensions normally with Pythagorean theorem. Actually, we can measure distances in other dimensions, higher dimensions, 3rd dimension, even 4th, 5th, and 6th if you want to. There's ways to adapt this Pythagorean theorem, but it's only if your geometry is of a rectangular nature. And so when we think of, or if we think of this wall as being a flat plane geometry where there is horizontal and vertical to describe it, then this is a natural way of measuring distance. In something like the surface of Earth, however, which is rounded, the geometry is no longer flat. Pythagorean theorem no longer holds. And so if you were to take a ball or a globe or the Earth and draw a triangle on it, it's easy to convince yourself that those triangles, you can even have a triangle with 2 right angles in it. You know, and for example, if you're at the equator of the Earth, the equator is connected by a curved line called an arc length, but that's one side of a triangle. If you connect that to the North Pole, then both these angles are 90 degrees, because to get to the North Pole you have to travel 90 degrees north. However, they converge together and form a triangle. So there's a triangle with 2 90-degree angles in it, and the sum of the angles is obviously more than 180. So, you know, the geometry gets really interesting and kind of screwed up when you get away from our rectangular, you know, normal way of looking at things. All right, well, let's go ahead, and I want to present this proof of the Pythagorean theorem. So I'm going to erase the board and get started on that. Like I mentioned, the proof I want to show you is attributed to a United States president, James Garfield. Garfield, at one time, had an ambition to be a math teacher. Then he got interested in politics around the time of the Civil War, and the rest, as they say, is history. In 1876, he was a member of Congress, and one day several members of Congress were with him, and they were talking about things, and somehow got on the subject of mathematics, and he showed them this proof of the Pythagorean theorem using a trapezoid. Now the trapezoid is a four-sided figure, so think about the outside edges here. It's a quadrilateral in which 2 sides are parallel. The other 2 sides are not necessarily parallel. Of course, they aren't in this case. So if you look on the outside here, that forms a trapezoid. By using a trapezoid and dissecting it the way I'm going to show you, Garfield was able to prove the classical form of the Pythagorean theorem. Well, no one had ever done it that way before, and it actually got published later that year in an education journal in New England. Garfield ended up being elected president in 1880. And by the way, he was from Ohio. And in 1881, in the summer, he was shot by a lunatic named Charles Guiteau. And if the unfortunate tragedy of things is if they had just left Garfield alone, he may have lived, because he had a rather non-threatening wound in his body. But the doctors kept trying to find it, and they kept poking around in his wound with their unwashed fingers, and they ended up giving him a terrific infection, and that eventually killed him. And about 2 months later. So unfortunately, it was the medicine of the day that killed him, not so much the bullet. Nevertheless, Guiteau was hung shortly thereafter. So in those days, we didn't waste time hanging murderers like that. All right, so let's see what we got here now. This is a right triangle, sides A, B, and C. And, you know, pretend that this is any given right triangle. In other words, you make up any right triangle you want, then I can use it to build this trapezoid. So I'll take that triangle and I'll put it over here, side up, same triangle. And then when I connect these 2 tops, then we've created this trapezoid figure here. Now it turns out this has to be a right angle also. And is that obvious? Well, this angle and this angle are complementary. In other words, they have to add up to 90 degrees. This is 90, and so there are 90 degrees left. These two angles add up to 90. We say they're complementary. Now this angle appears over here, and since these two angles are complementary, they add up to 90 degrees, and this is a straight angle, 180 degrees total. That makes that a right triangle. So that's kind of nice to know. And because it's a right triangle, that means that this area in here is half of a square. So that ends up being an important consideration in this problem. All right, now the way to go about this is to add up the areas. And so if I took this triangle and that triangle, and suppose I just rotated this on top here, I would have a rectangle, wouldn't I? And what's the area of this rectangle using these two triangles? Well, the area is length times width, so this area is A times B. The inside area is half of a square. Since that's right angle, sides are equal. The area of a square is length squared, or length times length. It would be C times C, C squared, and since it's half, that area is 1/2 C squared.